Oh, okay, thank you. So I have been going over through the role of nuclear quantization for Ab-initio modeling of methyl iodide photo-dissociation. And so the goals of this project have been to compare experimental observables to static absorption spectra, for femtosecond transition spectra, and mass spectra distribution of products. And to do that, we need to find these things. We need to find the wave packet dynamics, plane wave basis for excited and static, localized basis for ab-initio static, plane wave basis of multiple molecules for static and excited, and um, localized basis for multiple molecules. And so the first thing that we did was we ran a Matlab simulation to figure out our wave packet dynamics. And so I will play that for us.
Can
And
you,
so,
yeah, please run it once again to explain what is going on.
okay, yeah. So basically what is shown is the probability of the the atom being at that state for a given time. And the summation of both of those two curves is shown in red above, and that's what will truly happen to the atom in a probability curve, of course. And so at towards the end, we can see that there are two peaks, meaning that there are two different states that this molecule could be in. And this is shown, oh, this is shown on this slide, where if you look on the right, we see that we have two clear paths that are shown. That is because of the two different hills that we have on the simulation. This is for when it's not excited. It shows that the bond length is roughly 2.1. And this has been confirmed by this paper. As we can see, we have very similar curves.
Can you go back and would you please explain what does it mean excited, not excited?
Oh,
And
that's the so by excited, basically what happens is when the molecule is energized, electrons will move into different orbitals that have more energy. And so this shows the probability that it's at a certain of the length of the bond, which is related to where the orbitals are.
why they're going from left to the right?
As more energy is put into the system, the bonds will grow bigger. So as time counts down, the energy increases.
Okay.
And then, so following that, we um, put in orbitals, and we did this through two different ways. We did this through a Gaussian view and one through a VASP view. And so there are differences with each, and I will highlight those here. So the first one, Gauss uses, I believe, 6 electrons for carbons, whereas the VASP, only uses 4. So there's an extra orbital in the Gauss view. So it basically has this extra little, almost looking S orbital around the carbon. And then we go on to HOMO -6. And there we have very similar orbitals in the VASP and the Gaussian view, which persists for most of it. So as we can see, similar again in HOMO -5, pretty similar in HOMO -4. I assume that's just the different percentage that is cutting it off at a certain area. HOMO minus 3 and HOMO minus 4 have symmetrical, or not symmetrical, this basically the same energy state. This is seen again at HOMO minus 1 and HOMO. HOMO minus 2, very similar again. HOMO minus 1. This HOMO minus 1 is the top part, as is better seen in the vast view, more especially on the next slide, is very similar to the idealized atom 5p orbital that we can see in the periodic table. And as you can see, it's the both of these show the same dumbbell but in different orientation. So
Can
if
I ask
you
a question?
yes.
Okay, just out of curiosity, why are you showing both vast and Gaussian? Is it just you wanted to compare, or did you have a specific reason?
Yeah, so we were comparing the two and looking at how those differed. Mainly we calculated both, and so we looked at similarities and differences.
Okay.
And so, as you can see, that dumbbell shape is more or less the same. Here's LUMO. It once again much similar, and then we have LUMO plus one. When we looked at the vast view, we saw that that area was near was close to the p hybridization, and so we were looking to see if there was a reason for that. Lumo plus 2 is the last one that we calculated, and so that is where we end with that. I have a question in chat.
And you can read it out loud just in case it's
Yes.
not following.
Dr. Ford now asked, how do the wave packet dynamics relate to the orbitals that you are showing? Are those orbitals used as input for the wave packet dynamics? Um, I I'm not sure. I don't think so, seeing as though we did these afterwards. So it'd be hard for me to wrap my head around that. They are we they are going to be used later on for the density of states and then photo excitation.
Okay. Samir, one can, if something is done later, then one can say it is used for interpretation of previous results.
Okay.
So if we go back to your slide with wave packet dynamics, one more, yeah, here. And if you connect, you make a vertical line from distance IC at 4 at equilibrium, and you make vertical line up, how would you interpret the points of intersection? The first one, the second one, the third one, are they connected to orbitals in some reason? Can we interpret this different potentials as related to the orbitals?
So like, yeah, if there is an intersection here, it would is that's where an electron is able to jump from one orbital to the next and can excite the molecule itself.
Okay, and if you do not start it, if you haven't started the dynamics yet, if you look only a slice of this figure for x equals 4, like going straight up and looking intersection, yes, intersection, keep going here, intersection, keep going, keep going, keep going, keep going here, and then keep going, intersections there. So those intersections, are they related to orbitals in some way?
Uh, yes, because aren't these each individual orbitals? So if you add that much energy, it'll hop from one orbital to the next one.
Very close. It would be better to say it's different pairs of orbitals, different excitations.
Okay.
Aaron, are you satisfied with this interpretation?
Yeah, I think so. So each line isn't like just HOMO or LUMO.
No, 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 no.
There.
Each line is either, so the lowest line is ground state configuration, and the excited lines correspond to pairs of orbitals, like promotion from HOMO to LUMO, or from like HOMO minus 1 to LUMO. So different excitations.
Yes, okay. Yeah, that makes sense.
Okay.
Another question, the specified orbital range of HOMO minus a number to LUMO plus a number, why did you choose these orbitals? So we went down to the bottom, and then so I know that the last one, I think VASP just gave us 11 orbitals, so we stopped there. That's basically how we chose those. In the movie, there are multiple curves. What does each one represent? We just said that they represent different pairs of orbitals. And then so here is what we found was the most likely transition. It was from HOMO minus 2 to LUMO plus 2. And we have overlaid the two orbitals on top of each other. And so what is shown is the electron is prompted from the spatial area of iodine to the spatial area of methyl. And we will try to look at if it changes interatomic attraction.
So if electron is promoted from iodine area to methyl area, then iodine will become positively charged?
Yeah, yes, because there would be basically one less electron in that area. Lumos slide, are you trying to say that there are sp2 or sp3 hybridized? Oh, that just doesn't go backwards. This slide, correct? I think we just noticed that the shape of the VASP orbital was very similar to the shape of a sp orbital that was or a p orbital that was hybridized over here.
David, would you like to give your comment in words, like what is suspicious or what is interesting?
Well, I asked the question entirely just because you have both of them written down on the slide.
I think that's just because we pulled the image from the net and it just had that on there.
But my suspicion is that you're probably looking at sp3.
Okay.
Mm-hmm.
They have very similar. If you just look at one orbital, they look very similar. It's just how they're orientated.
Mm-hmm.
Okay.
Yeah, this. Yeah, David. Thank you. This tetrahedral shape definitely prompts sp3.
Yeah. So sp3 would be tetrahedral. sp2 would be planar.
Right.
Yeah. Yes.
But
sp would be linear.
Uh-huh.
Yes.
And if we wait until about almost the last slide or very close to the end, there will be situations when these hydrogens perform so-called umbrella motion and they come into sp2 configuration.
Yes. Yes. So we made a density of states chart. And so we can see HOMO minus 1, they share the same energy value. And then we have LUMO and LUMO plus 1. And those are shown on the density of states. Then we have our independent orbital approximation. And so this shows for a given electron voltage what the relative probability is that it'll change, I believe, change the orbitals, and that was shown. And this 7 corresponds to the most likely one, which was this. I believe that was a question.
Lola, are you satisfied with the answer?
Yeah, I see. Thank you.
Okay.
And then we also compared this to previous research. First, we can see that our peak at 5 was very similar to what they have at around 5.5. So it was very similar to the peak that they have 5. And also that our little hump at 4 was what they also started to experience at roughly 4. And that was done experimentally as well as computationally. The dotted line there is experimental. The solid lines and dashed line is computational.
Right. Okay. Thank you.
Wait. Oh, that's weird. Something moved. Okay. So we then made a simulation of what would happen between if we put a bunch of these molecules together and excited them. And so the bond lengths are roughly around 2.15 to like 2.22. And so we then excited it and then we looked at what happened. So as we can see, they all start to expand due to an increase in energy. But I would like to highlight this carbon-1 iodine 33 bond because as we continued to, I skipped it. As we continue to excite it, the other ones move back and forth, yet this one continues to expand and basically completely dissociate from its methyl group. And this is shown by it getting considerably bigger over time. And so there is.
Can we go back to last slide there? So what is the geometry of the methyl group around carbon-1?
The methyl group at this point would be trigonal planar as it's not bound to the iodine.
So it will be mostly sp2.
Yes, correct.
In correlation to question of David.
Yes.
Okay. Yeah, please keep going.
So this umbrella motion that we were talking about is shown through this, as we can see the molecules. Here, I'll slow it down. The methyl groups as they are attracted to the iodine groups, that bond angle between the hydrogens and the carbons is changing, and so we looked at that, and that is where we found that motion.
I apologize. Maybe you had mentioned this, but is there a reason you specifically chose this molecule?
I was interested, not really the molecule itself, but I was interested in the photo excitation that was going on, and I was suggested this molecule by Dr. Killen.
Thank you.
And so what we have, this is a refresher of what we needed to do, and as of this is what we have done. We have completed the wave packet dynamics through the MATLAB calculations. The plane wave basis for one photo-excited molecule is represented in the VASP. The localized basis of one molecules was done through the Gaussian orbitals, and the plane wave basis for multiple photoexcited molecules is computed by VASP and then visualized by the VMD. And that was the movie I just played for you. And then continued, we noticed some similarities. Both the wave packet dynamics and the Ab-initio molecular dynamic approaches demonstrate the deorbition event where the carbon iodine bond is broken. And so that was something that we looked to include was how this bond was broken and as when we excited it. Some differences that were present was in the Ab-initio molecular dynamics. The CI bond is always defined, but if we go back to the wave packet dynamics, there is two possibilities as we can see here. There is two possibilities, but when we did it, we defined a point.
Can you go one slide back and maybe explain more about two possibilities?
Yes. So if we go towards the end of this video, there are two distinct humps on the probability graph, and so what that means is that it could be in either of those states, both relatively likely. But for the Ab-initio model, we just selected a point in there, and that could lead to, and that was a difference between the two types of models. Then another thing that was different was so in the wave packet approach, the carbon iodine bond distance has a distribution with two peaks which correspond to a superposition of several quantum states, whereas in the other way it was defined as one way.
Okay.
Thank you.
Oh, okay. Please join me in thanking Sameer for presenting and answering questions. And although there were some questions, the paper is open for discussion. If there are more questions, please go ahead and either ask or suggest what can be improved, or what seems missing for the unbiased glance. Oh, Steven just came, but the presentation is over. We are in the discussion.
Do I get to go again?
I know you had mentioned, I think in that little flow chart, you were going to do like mass spectrum, or at one slide. Do you still plan on doing that?
Yes, we do. It was this chart, correct?
Yeah, yep.
Yes. So, yes, we still do plan on doing that, and then we will, that we just haven't gotten to it quite yet. We've done this so far.
And then experimental observables, like, is there a specific paper, or is this just like you said off the periodic table, you had gotten like the orbitals? So, have you actually like looked at a paper yet, or no on the experimental portion?
I'm not quite sure on this one.
Okay, no worries.
Oh, let me translate a question of Mead, how I interpret it. So if we go to your close to the end, dynamics, or maybe last snapshot of the dynamics. Yes, here. So if you would try to interpret this snapshot as a mass spectrum, as distribution of products, which peaks, which products would you see in such mass spectrum?
This would probably be you'd probably have some CH3.
Uh-huh.
They need to be ionized, right? So it'd be CH3 plus.
Mm-hmm.
You'd probably see I plus,
Uh-huh.
maybe CH3I plus.
Okay, so at least 3 peaks for sure,
Yes.
and maybe some another noise. Me, does it satisfy your question?
Yes, yep, that is fine.
Okay. So more. Let's check if there are more questions in chat line. No. So before the meeting, I did share the PDF of this slides, and the editable PowerPoint is intellectual property of Sameer. But Sameer, if you feel comfortable, we can arrange sharing your PowerPoint so that anyone who is interested can type in comment or correction just inside your file.
Yes, that's completely fine.
Okay, yeah, we can do it afterwards. So more questions 1, more questions 2, more questions 3. Please join me thanking Sameer once again. So in 2 weeks there will be literature review by Boston, and in next week we can spend another maybe 15-20 minutes for Sameer's next edition of this talk, but in the form of a poster. So we'll discuss it one-to-one, but one can take into account feedback and combine slides from the one-by-one slide, one-by-one slides into one poster in electronic form, and then just show it in a shared screen and explain how you would explain it on the formal poster presentation. Would it work for you?
Yes, that should be fine.
Okay, so beginning of the next week group meeting will be practice presentation of a poster.
Okay.
Yep, we do not have the second speaker because there are some family circumstances, but let's wish her to prepare talk and present it tomorrow successfully. So meeting is done. Anyone who has a schedule is welcome to disconnect, and I'll stay online to chat if some one-to-one questions are appearing. Yep. Thank you.